This morning's lecture, I'm going to talk quite generally about probabilistic modelling, and then in the future lectures, I'm going to give you an introduction to how you go about setting up Monte Carlo inference. There's going to be more advanced lectures about Monte Carlo later in the course. So probabilistic modelling, I've given myself sort of one and a half lectures to talk about it, and there's quite a lot to cover, so I'm going to have to go fast. How many of you have one or more of these books on your shelf? Okay. How many of you have read a significant chunk of one or more of these books? Oh, wow. Okay. So it's a good job I'm not going to march through a lot of the topics. What I want to do this morning is mainly give you a couple of examples and just make sure that you don't fall into some of the same pitfalls I've embarrassingly fallen into during my PhD. So this isn't meant to be too complicated, so do stop and ask questions at any time. It's 9 in the morning, so what I'm going to do is start with a warm-up exercise, and there's a chance you've seen this before, but bear with me. Okay, so what I've got with me are 3 coloured cards. Pretend the purple is black. I didn't have any black card, and I didn't want to write P of P on the slides for purple, so these are black sides. That card has 2 black sides. This card has 1 black side and 1 white side. And this card has 2 white sides, okay? And there's meant to be no magic trickery. You can condition all of your inferences on everything I say being true. Okay, so these are the 3 cards, and they're defined on the slide. And what I'm going to do is I'm going to shuffle them, and I'm going to turn them over randomly, so there's no sort of preferred side to them. And I'm going to keep doing that so that you can't see, so that you're going to assume that they're all sort of randomized in which card I'm going to pick and which way up it is. Okay, and then what I'm going to do is just pick one of the cards and show you one of the faces. So you've got some data, you have a complete specification of what the process was that you've observed, and what you see is a black face, and I can put this down on the table here. Okay, so the question is, there was this process, you saw a black face, and what's the probability that this other side that I can see and you can't, on the other side of this black face, what's the probability that that face is white? So is it A, 1/3, B, 1/2, C, 2/3, D, some other number I haven't said, or Z, it's too early in the morning, I haven't given you enough time, you don't care, or otherwise you don't know. Okay, so you're going to have to vote for one of these options. Hopefully that covers all possible things you could be thinking. Okay, is the problem clear? I don't want you to sort of afterwards say, oh, it's not fair because you didn't specify the question well enough. Okay. The good thing about doing this exercise is it gives the latecomers time to filter in and sit down. Okay, so who doesn't know yet? You're too busy like drinking your water or having a thing. So you all know. Okay, great. Who thinks it's some other number I haven't said? Okay. Who thinks that it's 2/3? Okay. Oh, so about 4 votes for 2/3. Who thinks that it's 1/2? Okay. About 37 votes for 1/2. Who thinks it's 1/3? Okay. About 12 votes for 1/3. Okay. Now, one of the great things about summer schools isn't coming to see all the talks, because I've got a bunch of talks on video lectures you could be watching. You could be out in the beautiful morning Iceland. Why are you here? So rather than me rattling on, what I want you to do is talk to the person next to you, especially if you haven't introduced yourselves yet. Say who you are, and if you're an A person, convince them convince the Bs that they're wrong. If you're a B person, convince the A persons they're wrong. And by the way, if you're a C person, you are wrong. Have a chat. Let's see if we can reduce entropy and get some consensus on that. I'll give you a couple of minutes. Okay. So let's have a quick see if anyone's changed their mind. Who thinks A, it's 1/3? Okay, fewer of you than before, I think. Who thinks B, it's a half? More of you than before, okay. All right, that's interesting. So when you have a fairly simple setup with only like a few random variables and about the simplest observation that you could possibly have, there's an outcome which is going to be black or white. It's already not obvious how to do the inference. And you've read a whole chunk of these textbooks on how to do machine learning and probabilistic inference. And you're all sure that you know the answer, but a whole chunk of you are going to be wrong. And the question is it 6 of you are wrong, or is it like 44 of you are wrong? And you might not like the answer. And we could argue about sort of intuitive explanations all day. So for example, there are these 3 cards. But we've seen a black face, so we know it's not card number 3. So it's one of the first 2 cards, so it's 50-50. And if it's the first card, then we'll get a white side. And that sort of intuitive argument might lead you to this answer. There are other intuitive ones, like I could have said this question differently. I could have said, you see a face, what's the probability that the other side is a different color? And presumably your belief in that is the same, because you've seen a black face, and being a different color means white, and so it's the same question. But this whole setup is symmetric. So presumably if you had seen a white face, your answer to the question, is it black, would be the same. So there's only 1 card out of the 3 which has 2 different colors on it. So if you're going to answer what's the probability that you see the other color, that's only going to happen 1/3 of the time. And that intuitive argument might lead you to this unpreferred answer, which is in fact the correct answer. But you might not believe any of these sort of intuitive explanations because they're a bit woolly. So what we need to be able to do is very carefully be able to answer these questions so we're absolutely sure we're right. When I've asked this question at previous summer schools, this is always the way it turns out. A half is a really, really popular answer, and people are always really sure about it. And the only real way to be sure is to do some computation, or you shouldn't be sure, and Z is the correct answer. So what I want to do this morning is just remind you of some probability fundamentals. I don't want to spend too long on that, but I want to highlight some of the places where I've tripped up in the past, and quickly say how to answer this question correctly. And then go on to a more interesting problem. So I'll have a data analysis problem from physics where we'll go through exactly the same sort of reasoning and do something more interesting than predict the color on the other side of the face, which happened to be black, by the way. So we'll see how far I get with that this morning, and in the future lectures I'll get on to sort of more general stuff about machine learning and inference, but this morning is about the examples. Okay. So there are only 2 things you need to know in probability theory, and you already know them because you've read a chunk of these textbooks. But let me just talk over them so that I can show you how I like to combine them. So the first of the 2 rules that you need to know is the sum rule, or the rule of total probability. It says that the probability that I will have time to have breakfast tomorrow is the sum over all of the sort of possible ways that can happen. The probability I'll have time to have breakfast tomorrow, given that I'm sensible and have an early night, because I'm giving a lecture first thing the next morning. But I also add on, there's a different way I'll have time to get breakfast tomorrow, which is that I go out really late and drink lots, but I still manage to set my alarm and get up. So there's all sorts of different ways that something can happen, and I add up over all those options, and I get the probability of the thing I'm interested in. Humans are really bad at doing this correctly. There's an interesting cognitive science here. You say, what's the probability that Bob will get fired from his job? And people might say something like, oh, Bob's sort of good at his job. He's not likely to get fired, 1 in 1,000. And then you say, what's the probability that Bob is going to be involved in some sexual misconduct scandal and will get fired from his job? And you go, oh, that sounds plausible. 1 in 100. and that term is just one term in the sum that gives you the thing on the left. That number has to be less than that number. But people will tell you that that number is 1 in 1,000 and that number is 1 in 100. So dealing with probabilities intuitively is hard. So remember the sum rule. Now, the other thing that is worth flagging, which is really just an excuse for the rest of my slides, is that probability notation is universally awful in the literature. Here I've been super explicit. I've said there's an event, capital A, and it takes on value little a and stuff. And if you do that throughout all your notation, it ends up incredibly cluttered. So I'll tend to compress it or overload it like that, with the intention that you kind of know what I mean. The problem with that is it's totally ambiguous. So, I'll have P of A, which means the probability that event capital A takes on value little a, and I'll have P of B, which means something totally different, the probability that event B takes on value little b. Now, if A happens to be 5 and B happens to be 5, that does not imply that these things are the same, because these things are like totally different functions of these numbers, right? So reading probability can be a pain because you've got to kind of know the sort of the convention. There's another thing that's worth saying about this rule. If you've got any identity in probability theory, this equation is true for any variables A and B. There's something you can do, which is go in and condition every term in the equation with another variable. So this is true for any variables A and B. It's also true for any variables A and B if it happens to be a Monday. So C says it's a Monday. And it's also true if it's a Tuesday. So you can go in and condition an identity and you get a new sort of more general identity. Okay, so that's the first of the only two rules you need to know. And the second rule you need to know is the product rule. So it says that you can consider learning information in different orders. So if you want to assign a probability to the fact that Bob gets fired and is involved in a sexual misconduct case, you could first discover that he was involved in a sexual misconduct case and sort of estimate what you thought the probability of that was, and then compute the probability that given that he'll be fired, which is presumably a high number if you're in a sensitive company, and multiply those two things together. Or you could first use your estimate that he gets fired, and then once you look at the people that get fired, you go back into their file and work out what happened, and you sort of predict what's the probability that I'm going to discover when I look back that he was involved in a sexual misconduct case. So you can go through the events in any order and piece together a joint probability however you like. Okay, now as with the sum rule, as with any rule, you can go in and condition every single term in the equation on another variable and you get a more general identity. Thank you. Okay, now I've got one that does the slides and one that does the pointers. It's going to be confusing. All right. Another thing about this equation to understand is that here A, B, and C could be individual outcomes. So it could be Bob gets fired. It could be what's the outcome of seeing something, is it purple or white? But they could be whole bags of variables. So in this equation, A could be a whole collection of several outcomes together, which I'm labeling A. So if you apply this rule multiple times recursively, you can unpack a joint probability into a series of probabilities involving individual variables. So the joint probability over 4 variables, you can compute as the probability of the first variable, the probability of the second variable, given that, the probability of the third variable, given the ones you've already considered, the probability of the next variable, given all the ones you've considered, and so on. So that's something that if you don't know how to derive for yourself, you should go and do that as an exercise, and you might have seen before. So those two things are really the only rules that I think I ever use on a day-to-day basis. But you might have seen combinations of them that you're more familiar with. So the first of those is, of course, Bayes' rule. We just get the two equations on the right-hand side and divide by P of B, and we get Bayes' rule. So Bayes' rule is nothing controversial. It's just some identity in probability theory. It's correct. There's no argument about that. The only argument is about how you use it, and it's irrelevant whether you actually explicitly use Bayes' rule or whether you represent your probabilities in some other way. Any controversy is about what you attach probabilities to, not the fact that we happen to use this equation. I actually very rarely use this equation, I think. Another way of writing this down is, if I'm interested in predicting A, given some data B, then on the right-hand side, the top two probabilities are things involving A. So as I vary A, as I consider the different possibilities, the things on the top are going to vary. And the thing on the bottom is, of course, just a constant. So often in maths, it's good to sort of just drop constants and work them out at the end. So I'll usually write that the probability of A that I'm predicting given data is just proportional to the stuff on the top, which is the joint probability. And so in David Mackay's textbook, he says that the probability of anything you want to know is proportional to the probability of everything. And maybe A and B isn't everything. There might be other variables in your problem apart from the things you see and the things that you care about predicting. So if there are other variables, C, that you want to include in your maths, C doesn't appear on the left-hand side, so it must be a dummy variable on the right-hand side. We must have to sum over it. So the way to get any probability that you want is to write down the probability of everything, the joint probability over things you care about, things you've seen, and anything else. You sum out the things that you don't want to appear on the left-hand side, and you're done. So for many purposes, that can be the only rule that we actually need for data analysis, and that's the one that I often write down, and it's the one you often write down if you start doing approximate inference. Okay, so let's solve this problem we started out with, the card prediction problem. So we've got these cards and we've got this randomization process. We see a black face. What's the probability the other side is white? And it's worth practicing this sort of simple exercise. See if you can write computer programs to work out all of the probabilities and check them using different formulae to see that they're consistent and they're right, and that you definitely know what these formulae mean. As you practice, you often can find yourself going around in circles. So I did this myself when I was first learning this, and I see a lot of students do this in their homework assignments. They say, I want a probability of the second face being white given the first face is black. This is a conditional probability. I know, I'll use Bayes' rule, because Bayes' rule is the rule that gives me conditional probability. So they write down Bayes' rule, and they go, okay, to get this probability, I'm going to need to know the probability that the first face is black given that the second face, which I haven't seen yet, is white. I don't know how to get that either. I know, I'll use Bayes' rule, and so you write down Bayes' rule for that, and then you need to know this one again, and you don't get anywhere. Right, so Bayes' rule isn't this sort of magic formula that like answers all questions. It's for a particular sort of question. It's for, I've got a generative forward process that I understand, and I can write down all of the probabilities, and it will allow me to turn that process on its head and understand what caused the things I see. And this question isn't a question of that form. The generative process that I showed you involved cards. I said I've got these 3 cards, and I showed them to you. And this equation doesn't contain the cards. It doesn't contain the generative process. So Bayes' rule isn't the right solution. So the way to go about solving a problem is to first write down actually what's going on. You sort of forget about the question that you've got to solve for the minute and just say, what's a mathematical description of what happened? So we've got these 3 cards. I picked one of them uniformly at random, so that means let's give the cards a letter. Lowercase c is going to be the choice of card. The probability of that card choice is uniform, if you believe me. And then you saw one of the faces at random of the card. So if I had picked card 1, there's a half chance you'd have seen the black face. If I had picked card 2, you'd have definitely seen a black face. If I had picked card 3, there's no way that could have happened, so we know it's not card 3. Okay, so here we now have a complete description of the generative process that led to this observation that you saw a black face. And this is something we can invert with Bayes' rule. So we can now write down Bayes' rule. We can try and invert what's going on and say, what's the probability, our beliefs about the underlying card given the data we got? We can write down Bayes' rule. We can substitute in the numbers, and we get the answer 1/3, 2/3. We have a third belief that it's this card that's black on one side and white on the other, and so therefore when we turn it over, there's a third chance that we'll see a white face. Okay, and that disagrees with the intuition of most of you, or at least the knee-jerk intuition, even after you got to talk about it for a bit. So sort of that, at this point, there's some sort of outrage. It's like, but there were 2 options. It was either this card or this card, so surely it's 50-50. And There are two options. It is clearly one of these two cards, but the likelihood of this card is 2 times higher. This card has a 2 times higher probability of generating the data you saw than this card. And so given the data black, you should prefer the data generating machine that sort of spits out that data more often. Okay, I have a whole load more slides on like excruciating detail of how to like relate this to other problems. So these slides will be online, and I encourage you to go through those if this isn't the sort of exercise you've done a lot. One more slide on the cards. This is the approach with the probability of everything. We say what we want is the probability that we want a distribution over what we'll see next, given that the first side is black. That's proportional to the probability of everything with things that don't appear here summed out. So we write down the joint probability over the card choice, the first side which we've seen as black, so we can put that in, and the next side that we haven't seen yet. The card doesn't appear on the left-hand side, so we sum it out. Here is a table of the probability of everything. So there's a third chance we'll get the card 3, the white card, and we'll see a white faces. There's a third chance that we'll pick the second card, and both sides will be black. And then there's a third chance that we'll pick the first card, and that probability is split 2 ways into an option that you'll first see the black face or you'll first see the white face. So, and all the other options are impossible. So you just write down those numbers, you substitute them into this equation, and the answer drops out immediately. So it seems like massive overkill for this problem. It seems like a lot of work to go to. But on the other hand, it's not that much work. This is about the most compact way I can get to get the right answer here. And if you don't do this, you get it wrong. So I'd encourage you, when you've got a problem, it's good to have intuitions about it and make guesses, but also just write down what is the joint probability over all the variables, and you'll get the answer right. Okay, I'm going to do one final bit of probability theory, and then we'll do something more interesting than showing cards. So what I'm going to show you over the next 3 slides, I'm including in this lecture because it's something I have screwed up repeatedly and wasted hours because I've forgotten about the problems on these slides. So it's a reminder that when you've got probabilities over real valued variables, they're not quite the same thing as the nice discrete probabilities of there's a half chance that you'll see a black face, or there's 2 options, black or white. So if you've got a real valued variable x, then there is a nice discrete probability that it lands in some bin between A and B. But usually what we write down is the probability density over that. And when I remember, I use a lowercase p to remind me that a density is not the same thing as an uppercase p, a probability. But as I said about notation, don't expect any consistency when you read across papers. But careful people will often use some sort of notation to say that a probability density is not a probability. A density is something you integrate over a range to get a probability. So the probability that a variable lands in a narrow bin of width delta, so around a value x plus or minus delta over 2, is a density multiplied by a bin width. And these densities don't satisfy all of the properties that probabilities do. So in particular, if my bin width delta is really, really narrow, but there is quite a large probability of landing in that bin, then this density could be bigger than 1. So this product here is a probability. A probability can't be bigger than 1 because probabilities add up to 1. But if you've got a very narrow bin, this product could be less than 1, but the density could be much bigger than 1. So that's the first sign that you've got to be slightly careful with them. Here's the most obvious place that real valued quantities and discrete quantities don't behave the same way. So let's first look at a discrete setup that is nice and well behaved. In the top left, I've got a distribution over 3 numbers. So x takes on values 1, 2, or 3, the integers, and it has probabilities a quarter, a half, a quarter. Okay. I'm going to create a new variable, z, which is 2 times x. So z is also a discrete variable. It takes on values 2, 4, or 6. And these bars just get stretched out. They stay the same height. They're a quarter, a half, a quarter. And the probability that my new variable z is 4 is just the probability that the original variable was 2, because if my original variable was 2, then when I double it, I'll get 4. And so that middle bar moves from 2 to 4. So transforming discrete variables is straightforward and obvious. If you transform real-valued variables, it's not quite the same. So in the lower left, I've got a probability density over a real-valued variable x. The support of this distribution is roughly between 0 and 4. Most of the probability mass is peaked around 1. And if I draw a sample from this distribution, I'll get some real number, like 3.62158 and so on. And now I'm going to create a new variable z by, again, doing the same thing. I'm going to say my new variable z is just 2 times x. I draw a sample from x, and then I double it to get z. And that means that instead of my distribution going up to about 4, it's going to go up to about 8. Instead of the values being peaked around 1, they're going to be peaked around 2. The whole distribution is smeared out to the right. Now, probability densities integrate to 1, just as probabilities add to 1. So the area under this curve is 1. This curve is twice as wide, and the area still has to be 1, because this is still a probability density, and so obviously the curve has to be half as high. Okay. So what that question?
Isn't the probability of any one particular value 0, because there are infinitely many real numbers, and you always have to take a range, and then if you change the scale of the range, then you would probably also multiply the size of the range by the same number, and you still end up with the same probability.
Okay, so the question is saying, isn't the probability of a single value 0? That's absolutely correct. These lowercase p's aren't probabilities, they're the densities. And what I'm doing is talking about what happens to the probability densities. Because usually what people do is they say, okay, probability densities, these lowercase p things, they're not really probabilities. But in most of our equations, if we just pretend they're probabilities and ignore the difference, everything works out. And that's usually true. So what I'm doing is just pointing out places where the densities don't behave quite the same. And yes, obviously, if you discretize things carefully and consider probabilities, then they will behave the same as probabilities. What I'm saying here is true, though. The densities don't behave in the same way as the probabilities. So the density that z is equal to 4 is not the density that x is equal to 2. So these red bars are in equivalent places of the distribution, and the distribution is halved in size. So the probability density that z is equal to 4 is half the density that x is equal to 2. And this might seem like a bit of a pedantic point because, you know, what's the factor of 2 amongst friends? We usually drop constant factors through our math anyway and make them up at the end. And that's true. If all you're doing is linearly stretching your distribution, you're probably not going to run into problems. What you have to worry about a bit is if you non-linearly stretch things. So if I have a transformation which scrunches up some bit of the x-axis but stretches out a different bit of the x-axis, then that could have a dramatic effect on the densities. It could totally change their shape. So the maths for dealing with that is, just as was said in the question, you consider what happens to little elements of probability, because as probabilities we know how to deal with. So if you have a little element on the x-axis, it has probability equal to its density times the width of the element. If you track what happens to that element as it goes through the transformation, then the probability of landing in the new element on the z-axis should be the same. So for a narrow, very narrow bin width, this equation should hold. And if you take limits, and you're a bit more careful than I usually am, you get that the correct way of converting densities is to multiply by what's called a Jacobian term. So that half on the previous slide is the result of differentiating the equation z equals 2x. But if you had a nonlinear equation, this derivative would be more complicated. So this might be something you're familiar with and you've done a lot before. If you haven't, I would work through some examples and sort of check you know how to change variables correctly. So as an example, let's say I'm interested in the probability density over a variance in my model. My model has some parameter called sigma squared, which is a variance. It could be that I've decided to put a prior on the log variance because I think that's a more natural way of specifying a prior. So I don't know whether this variance is going to be 100th, a 10th, 1, or 10, or 100. They all seem equally plausible. So I'm going to put a uniform prior on the log variance between say, 10 to the minus 3 and 10 to the 3. So if this density is uniform, the density on the variance itself is incredibly non-uniform. You started out with a flat prior on the log variance. Your prior on the variance has a whacking great peak at the smallest value. If I did a different nonlinear transformation, I could put the peak at the largest variance instead of the smallest variance. So the probability density, its shape, doesn't necessarily have any meaning. You can reparameterize your variables and put the mode of the density wherever you want. So if you're ever doing something like maximizing a probability density, you've got to think, am I doing this in a sensible parameterization? Because the parameterization I'm using is going to change my answer. Okay. Here's the other, another way of looking at transformations. And this slide is sort of where, and the next slide is where I really made the mistakes. Let's consider this same setup. We've got a variable z, which is double the original variable. So before we were looking at the marginal distribution, p of z, which was this transformed distribution. Now I'm going to look at the conditional distribution. Given I know x, what's the distribution over z? So this is sort of a totally certain distribution, because given we know x and this is deterministic, we also know z. So in the discrete world, the probability that of z given x is an indicator function. This is sometimes written using a 1, that z must be equal to 2x. It's also written using what's called a Kronecker delta that says z must be 2x. And so this distribution has probability 1 that we've got the right answer and 0 otherwise. Okay, so that's totally simple. We can deal with the numbers 1 and 0 in our maths, and we never have any problems. The continuous version, instead of having a Kronecker delta, has a Dirac delta. So we have this funky pseudo function that says z must be equal to 2x. And you can think of this as the limit of a Gaussian distribution. So we've got a super peaked distribution on z, and that distribution has mean at 2x, but it has 0 width, or incredibly narrow width. And so that's how the densities have to behave in order to deal with it in our maths. And this Dirac delta is not the same as the Kronecker delta. So in particular, if I evaluate the probability density that z is equal to 2x, then that density is not 1, it's infinity. So normally with any probability density, as was pointed out, the probability of any individual number is 0. And in this case, we want the probability of an individual number to sort of be certain, and the only way to make that happen with densities is to set the density to infinity, to have this Gaussian so narrow that its peak shoots up to infinity. And you should know to be incredibly careful wherever your math has infinities in it. So if you ever have equations with multiple delta functions in them, don't just put slashes through them to cancel them out, because they're all infinity, and some of them might be bigger infinities than others, and that's a real problem. Okay, so the only safe thing to do with delta functions is integrate them. So here's a demo of how you actually use delta functions, and it marries together the two things I've said so far. So we've got this situation, z is equal to 2x, and the conditional distribution is this delta function. Let's return to the original question. What's the marginal distribution over z? And before I just wrote that down, I had some argument about stretching, and I just said, here's the answer, it's involves a Jacobian. But we should be able to get that using our normal 2 rules. So here's the sum rule. It says that the probability of z is the probability of everything with the stuff we don't want summed out or integrated out, because these are densities. Okay, so if we substitute in the probability of everything using the product rule, we get our original probability of x and this delta function, which is the conditional distribution. And we have an integral to do. So it must be the case that that integral will give us the right answer. And you have to be a bit careful when integrating delta functions. and this is something I've got wrong many times, and I've seen people cleverer than me get wrong, it's tempting to look at this integral and say, I know how to do this. This delta function says that z is equal to 2x, or in other words, x is equal to z over 2. So all I need to do is go through the integrand and replace x with z over 2. And that would tell me that the probability of z is the probability that x is z over 2, which we've already discovered is the wrong answer. So that is not how you integrate delta functions. You can't just solve an equation inside them and then replace that equation throughout. You have to be a bit more careful than that. So the correct way to integrate delta functions is to do a change of variables. This 2x is problematic. I don't know how to deal with it. So I'm going to replace that with a new variable u, do the change of variables stuff you do in calculus classes, and then you get a new integral involving u. And that integral has a simple delta function where you really can just go through and replace u with z or z with u wherever you like. And when you do the integration carefully, you end up with the same answer as the Jacobian argument. So it's incredibly easy to get these integrals wrong. If you haven't done them before, just remember that. And when you do have to deal with the delta function, stop and think, oh, maybe I should look up how to do this. Or if it's something you're interested in doing, check that you can work through this and get the same answer. I often sort of do stuff with Jacobians and then do stuff with integrating delta functions, which are really equivalent, and just check that I get the same answer. Okay, so everything that goes wrong with probability densities is really where you have determinism, where you say there's a strong constraint, this variable is equal to some function of the other variable. And it might seem like a bit of a pedantic point, but the reason I chose to put it in the summer school is that I see it a lot. So I've recently done a lot of changes of variables. It turns out that a lot of how to improve approximate inference algorithms in machine learning can be, how do I represent my model in the first place? And sometimes, instead of coming up with a new algorithm, you can run an existing algorithm after doing a change of variables, and you'll get better results. And so you have to know how to do changes of variables correctly. There's a lot of machine learning that has constraints on manifolds. So we often have variables which are themselves probabilities, so they live on a simplex. Or you might have variables that live on the surface of a sphere. So we have constraints. And whenever you have constraints, that can cause problems. So if you have 3 variables, x, y, and z, but they have to live on the surface of a sphere, then the probability density on that sphere is infinite, and you have to be a bit careful. Gaussians with low-rank covariances also have infinite density. Whenever you do Markov chain Monte Carlo, where there's some sort of hard constraint, you're following some deterministic dynamics, or you're constrained to do your update in a subspace, then you have all of the technical issues that I've been describing, and you have to be a bit careful. Okay, so what I want to do next is use the stuff we've seen so far, how to write down the probability of everything, be careful with deterministic variables to solve a more interesting problem. Should just pause for breath for a minute. Are there any questions on what I've said so far? Is it all clear? Okay, great. So I want to tell you about the sort of initial versions of something I've done with some astrophysicists. And they're motivated by this satellite called Gaia, which launched in December. I was at dinner with these astronomers in December when the satellite was being launched, and they spent the whole evening checking Twitter to make sure that the satellite didn't blow up as it was being put into orbit. And happily, it survived, and it's there, so there will be data. And it's going to make accurate observations of billions of stars. And it's going to be a several-year mission, so it can look at the stars, and then it can look at them a year later, and they will have moved a little bit. So we'll get some velocity information on the stars. We'll see where they are, and we'll also see where they're going and how quickly. What the satellite won't get to do is see much of the actual dynamics of the stars. So these stars could be on billion-year tours or multiple million-year tours through the galaxy, And in 1 year, you don't get to see any of that sort of trajectory. You just get to see sort of instantaneously which way it's moving. So all the sort of grant applications for this mission said, oh, we're going to sort of understand the dynamical systems these stars are undergoing and sort of infer what forces they're experiencing and things. But it's not obvious whether, given this sort of snapshot where you only see instantaneously how things are moving, whether you can actually understand a dynamical system. So what I want to show you first is the simplest version of this problem and how you would go about solving it using probabilistic modeling techniques. So the simplest version of this problem is our stars have conspired to conveniently be all in a straight line. So we've only got a 1D universe, and that will make our maths a lot simpler. And we've got a black hole. So they're experiencing some force, but we can't sort of directly observe where that force is coming from or how big that force is. So we assume there's a central black hole and the stars are oscillating around it. So the center of our galaxy has a black hole, and around it there are stars orbiting, and the nearest star takes 50 years to go around the black hole, which has an elliptical orbit just sort of like a planet in our solar system has going around the sun. So this is something that actually happens. Stars do orbit black holes. And in 1D, they would undergo what's called simple harmonic motion. It would be like they're attached by a spring to the black blob, and they just oscillate back and forth. I'm ignoring the fact that messy things would happen as they tried to go through the black hole, but this is sort of an idealized version of the problem. So the maths works out that the mass of the black hole determines the frequency with which the stars oscillate around the black hole. So you will have some stars which ping back and forth a short distance, and you'll have some stars which ping back and forth a really long distance, but they'll all do so with the same time period or the same frequency. And so what we'd like to do is estimate the mass of the black hole or estimate the frequency with which the stars are moving. So if we got to see the stars moving around, we could just watch them for a while and we could measure the period of their motion and we could go, okay, now we know the mass of the black hole. That would be nice. On the other hand, if we only see a snapshot, it's not obvious that we can measure the mass of the black hole. So if all we see is, here are the stars, they're in these positions, and here is their current velocity, can we sort of tell what's going on? So if we look at an individual star, it might have a really small velocity. And that might mean, okay, this is a weedy black hole that's not exerting much force, and this thing is moving really, really, really slowly, and it's going to have a massive tour, and it's going to have a really low frequency. So we might infer from looking at a star that the black hole is not very massive. But there's another explanation. This star might have a tiny velocity because it was moving out this way, and it's just turning around to move back again. And no matter what happens, if you're at the edge of your motion, you're turning around, you're going to have a small velocity. So it could be that if we were to wait a bit, this thing would scream, accelerate really fast through the black hole to about the same distance on the other side, turn around and scream back through again. And it could be a really, really massive black hole. So from any individual star, you can't know what's going on. If all of the stars happen to have really small velocities, we probably could say something. Because if they all had small velocities, we probably think, yeah, there isn't much force in the system. It's probably a quite light black hole. The alternative explanation is that every single star is coincidentally just turning around at that same moment, which seems sort of unlikely. And so the frequentist would say, I'm going to set up a hypothesis test, and I'm going to reject the hypothesis that this is a heavy black hole, because in order for that explanation to follow through, I need the suspicious coincidence of the phase of all of their orbits to be in exactly the same place, which I can reject with probability 0.05. Okay. What we'd like is like a proper probabilistic way of solving this problem. And the physicists who sort of first thought about this problem thought that there couldn't be a Bayesian answer to this problem. The answers they had involved saying, we're going to reject explanations where all of the stars have the same phase of their orbit, but there's no way of doing that in the Bayesian paradigm because your prior would say that's just as good as any other setting. Okay, so the correct Bayesian way forward is to build a model, so we'll have to understand a bit of what's going on. There's a very, very small amount of physics here, but if you do any sort of work with collaborators in the sciences, you'll probably have to sort of deal with more complicated maths than this. So here is the equation for simple harmonic motion. This is the equation of motion of the stars. It just says the position of an individual star, the nth star, is a sinusoid. The sinusoid has height a, this is an amplitude of the motion. It oscillates with common period omega, so all of the stars have the same frequency omega, and there's a different phase. So here, over time, are 3 stars oscillating around. The blue one has a small amplitude, the red one has a large amplitude. They have the same frequency because the distance between the peaks is the same, but they have different phases, so the peaks aren't in the same place, they're not in the same time. Okay. The velocity is just the derivative of the first equation with respect to time, and it's the slope of these trajectories. So if we got to see all of these trajectories, we'd just measure the distance between the peaks and we'd read off omega. What we actually see, our data, is this stuff at the end. At time 0 now, we get to see the current positions, so we get to see the 3 positions, the position x, and the little lines coming out are tangents to the curves. We get to see the current velocity, and that's all we see. So from that little bit of information, we're trying to infer all of the rest. Okay, so if I evaluate these equations at time equals 0 to get these final positions, the math looks a bit simpler. Our model is that all of the positions are equal to this equation, and all of the velocities are equal to this equation. So if we knew the amplitudes and phases of all the motions, and we knew the frequency omega, we'd be able to write down deterministically what our observations would be. Okay. Unfortunately, we don't know omega, that's what we're trying to estimate. We also don't know any of the phis or any of the amplitudes. We don't know those without seeing more of the motion. Okay. Question?
Oh, sorry, what's the W log?
Oh, sorry, that says without loss of generality. So that means I could have chosen to evaluate these equations at time equals 10. I could have defined now to be time equals 10, and then it would have just changed the definition of the phases. But why make life hard for myself? So I'll define my phases so that now is defined to be 0, and then my maths will be simpler. Yeah, please do just call out if you have a question, because I'm not very good at spotting hands. Okay, so what we want to do is build up a complete model of everything, and I'm just going to throw that up on the slide and unpack it. So how many people are familiar with this sort of graphical description of a distribution? Yeah, so only about half of you, or less than half. So I am going to talk more about graphical models later, but I'm just throwing you in at the deep end here because I think it's fairly intuitive what these things mean, and then we can talk about them more formally later. So this is what's called a directed graphical model. The observations x and v are in a shaded circle. So the shading means this is something we observe. You'll also see in papers a double circle where they don't want to use shading. There's different notations. And those quantities, those observed quantities, are created from the other quantities we don't know, the frequency, the amplitude, and the phase of the motion. And the diagram doesn't say how they're created, so we'll separately write some equations that say this is how they're created. In a lot of graphical models, these arrows are not deterministic links. They're usually a probability distribution for some settings here. There's some distribution over what you'll end up. Here, we've got delta functions that say we know what these things will be given the parents. And for one star, our graphical model would just be these 4 circles and the arrows joining them. But what we've got is multiple stars, and so we have this plate or the box just to save some writing. So I could have said my variable is omega, and I've got amplitude 1 and phase 1, and that leads to x1 and v1 position, the position of the first star, the velocity of the first star. And then it's like, oh, I've actually got 2 stars. So that has an amplitude as well, and it has a phase, and it has a position and a velocity. These are more variables, which are created like that. And I have a 3rd star, and it has velocity and a phase and a position and a velocity. They're generated like that. And that gets quite messy, especially when you have a more interesting model than this one. So this plate is just a shorthand for this writing out of everything. It's saying copy everything inside here, write it out n times for the n stars, and join the observations of every single one of them to the common frequency. So every star has its own amplitude and phase, but they all share the same frequency. Okay. Now, this diagram tells you what the form of the probability of everything is, and the probability of everything is what we're aiming for. So the joint probability over the frequency that they're all oscillating with, and all the amplitudes, phases, positions, and velocities. And the rule for decomposing or writing down this probability, given this diagram, is to first write down distributions over all of the parents in the graph, the things that don't, the root nodes that don't have any parents. So we write down there's a probability of omega, there's a probability over all the amplitudes, a probability over all the phases. And it's all very well me writing this down, P of omega, but then I'm going to have to specify what that distribution is. So in other words, I'm going to have to specify a prior probability over, before the data came in, what do I think about the frequency of this system? I'd have to specify what units I'm going to measure physical quantities in, like amplitudes and frequencies. Am I going to measure them in hertz or millihertz? Amplitudes, are they going to be in parsecs or meters? And I will have to make some choices. So, for example, the frequency, given a random physical system that I don't understand, I might be tempted to say, well, the frequencies could be, I've no idea. They could be 10 to the minus 3 in the units I'm using. They could be 10 to the 3 in the units I'm using. I don't know. So it's natural to put a uniform prior on the log of the value. If you've got a positive quantity, taking the log of it is often a good idea, and then you could transform that to get this density. The phases take on values between 0 and 2 pi, and as I argued when I set time equal to 0 without loss of generality, I don't really have any special value for the phase, so it makes sense to just put a uniform prior on that. And we're going to return to this. This statement is a big mistake, but I will lie to you and say it anyway at this point. The amplitudes of the motion, just as with the frequencies, it's a physical positive quantity. It makes sense to just put a uniform prior over a large range. I don't know a priori whether these things are going to be oscillating really closely to the black hole or taking massive, massive tours. So I'm going to not be dogmatic about the order of magnitude of this quantity and put a uniform prior on it. Okay. And then to complete the probability of everything, we've written down our priors. We then go to the nodes that have parents, and we write down the probability of the things in the node, so the probability of the observations, given all of the things it's attached to. So here's the probability of the observations, given all the stuff we don't know. And that whole product there is, for this model, the joint probability. So it's a specific form that's simpler than the one you'd get if you just wrote down the product rule for a general probability distribution. Question?
So you made the point earlier on that this is a density and not an actual probability.
Yes.
So the argument why we can treat this with probability theory stuff we did earlier, that in effect you have an integral with some choice of range, and we can just compare the inner part of the integral and say, well, forget the actual integral part of it. Yeah, so the question here is, there's a density here, like, how is that going to be okay? And yes, I'm going to have to be able to consider little bins of elements close to the omega I'm evaluating or close to any of these real numbers. And if I can't do that, I'm going to have to be very careful. So yeah, as soon as I start to do anything with this equation, you've got to be slightly careful. Okay. So at this stage, I've specified everything. I've put priors on all the things I don't know. We've written down the physical process of how these things are generated.
And this distribution here is a couple of delta functions saying that x must be equal to that and v must be equal to that. So now if I want to infer omega, I can just apply the normal rule. I can say the probability of omega given the observations, and not anything else because I don't know anything else, is proportional to the probability of everything with the stuff that's not on the left-hand side integrated out. So this is the point that I'm going to have to be careful. This probability of everything contains delta functions, and when I do those integrals, I'm going to have to be careful. And by all means, go away and have a go at that. It's perfectly possible, but it's a bit messy and horrible. Another way that you could go about it is before you substitute in all of this stuff, you could sort of just try and do some of the integrals in general, and then your maths might be simpler. So if we split this thing up into the probability of omega and the probability of everything else given that, these integrals in general for any joint distribution just get rid of all the amplitudes and the phases. So we can reduce this equation to this equation. And this probability density here, if you know the frequency, what's the density of the position and the velocities, this is a deterministic transformation of your prior over the amplitudes and phases. So if you know the amplitudes, phases, and omega, you know these things. So you can write down what this density is as using the Jacobian change of variables trick. I'm going to give you a link later that goes through all of the maths of this, but I'm just saying that this is correct. I haven't lied to you. You can write down the probability of everything and do calculus, but there are some shortcuts that make the maths a bit easier, and I'll give you a link to how to work through that. Okay. So here's what happens if you do all this stuff. Here's the results of a synthetic experiment. I generated 100 synthetic stars, and I gave them random amplitudes in some range, say between 5 and 10. And I gave them random phases, and I pretended to observe them. And the system had a true omega of 1, so that's the red line, and my posterior is this magenta thing. So the truth is contained in the posterior. And at this point, as often when you get results from a machine learning system or from a statistical method, you go, well, how have I any idea if that's good or not? It's like, okay, I've got a posterior, but like, so what? So it's good to have something to compare it to say, is this result good? So there are different ways of doing comparisons. One thing you can do is compare to baselines. You can try and come up with a dumb thing that you could have done instead of your fancy method and hope you do better than that. And another thing you can try and do with any method is compare to an oracle. You can say, is there some way of cheating in this problem? And then I can try and see how close I'm getting to this sort of oracle performance, how well I could do if I knew a bit more than I actually know. So I'm going the oracle route here. And this gray distribution is going to be my oracle. So in my simulations, I drew my amplitudes between, I think, 5 and 10. It doesn't really matter, but from some narrow range. And in my prior, I pretended I didn't know I'd done that. So I said the amplitudes could be anything on a log scale between, say, 10 to the minus 2 and 10 to the 2. So in other words, I kind of used the wrong prior. My model said these amplitudes are going to come in with some large range because I don't know what the range is, but in actual fact, they came from a narrow range. And that could happen if I was analyzing real data. So the gray line shows the posterior I'd get over the frequency if I used the correct range over amplitudes, the range I actually drew them from when I simulated my data. And it's incredibly peaked around the right answer compared to my posterior. And it's tempting to just sort of say, oh, well, that's what happens if you sort of have the wrong prior beliefs. You end up with the wrong conclusions. But I'm a bit allergic to the term wrong prior. I think you can't have wrong priors. Priors are what you believe, and I didn't know what these amplitudes were, but I'm prepared to learn, and it should be possible for me, given enough data, and I had 100 data points here, it's quite a lot of data, it should be possible to get distributions peak to the close answer, to the right answer. And in this case, it turns out I've done something really stupid, and it's possible to do much better than this magenta posterior and get much closer to this oracle. And if you sort of take away one thing from this lecture, I'd really like it to be understanding what I've done wrong in the previous 6 slides. Okay, so here's the mistake. I had a prior over the log amplitude of one star, which was uniform over a large range between some maximum amplitude and some minimum amplitude. And I would stand by that. If I had to put the prior over one physical quantity that's positive and I have no idea what it's going to be, I don't think there's much else you can do. You could argue slightly that you'll use a log Gaussian instead of a log uniform or whatever, but basically you're going to have to pick something very broad, and there's nothing you can do about that. The mistake is that I extended this equation to write down a joint prior over the amplitudes of all of the stars to just be the product n times of the top equation. And that's wrong. I might believe that all of these stars fell in independently, and in the physical world, their amplitudes don't depend on each other. They didn't get to see each other. But that's not the same belief as the one I'm saying here. So let me explain why. You might think I have no idea what these amplitudes are going to be, and so I'm going to put a broad prior over the amplitudes of the 100 stars I'm going to see. And I'm going to say, that's fine, I believe you, guess what the amplitude of the first star is, and you'll go, it could be anywhere between 10 to the minus 2 and 10 to the 2. And then I'll say, okay, the amplitudes of the first 5 stars are 5.6, 7.3, 8.15, 9.2. And I give you a few numbers. You're not going to believe that the amplitude of the next star is still uniform on a log scale between 10 to the minus 2 and 10 to the 2. You're going to think, yeah, maybe the next amplitude is going to be around 7 plus or minus 3, because that's where all of the stars I've seen so far are. This independent prior refuses you to let you do that sort of learning. It says, it doesn't matter that you've seen all of these numbers between 5 and 10. You're still going to believe the next number could be anywhere. And that sort of refusing to learn from experience. It's not sort of a vague prior. It's an incredibly dogmatic prior. It says, I'm going to refuse to learn from experience, and I'm going to assume that everything comes from this very broad distribution, no matter what experience I have to the contrary. So what we need to do is fix up our graphical model. So here's our model on the left. And the mistake is that I've got here 100 amplitudes. This node here is actually 100 nodes because it gets replicated by this plate. And when you write down the probability of everything, you have to write down the distribution of the root nodes. So I'm claiming that I know the distribution that 100 things came from. And that's an incredibly big claim, when in fact I have no idea what distribution they come from. What I should do is what it says on the graph on the right. I should say, these amplitudes all come from some common distribution, which is parameterized by theta, and I don't know what that distribution is. So I don't know what the theta is. I don't know what the parameters of this distribution is. So as an example, I could say the probability of an amplitude given theta is, I could pick uniform on a log scale. I could insist that my amplitude is between theta 1 and theta 2, some range, and 0 otherwise. Sorry, this is a density. But what I don't know is what this range is, and I'm prepared to learn these numbers, theta 1 and theta 2, from the data itself. So it's sort of a lint checker. If you're writing down a graphical model, if you have a node inside a plate without any parents, be deeply suspicious. You're kind of saying, I'm really strongly knowing how all of these things are distributed, when maybe if I saw a few of them, I'd change my mind about how the other ones are distributed. And it's much safer to attach something common and shared to them that you're prepared to learn, so that you can learn amongst this population. So in the model on the right, the probability of everything does say that all the amplitudes are independent, but only given some stuff you don't know. And that stuff you don't know will couple your beliefs amongst the amplitudes, allowing you to learn between them. this bit here is maybe something weird that I do. I'm not sure whether people would do this in general. I've just put a blob here to remind me that I've asserted that I do know how these phases are distributed. So I'm going to assume that all the phases are independent, uniform between 0 and 2 pi. I'm going to assume these stars aren't interacting, which is a strong assumption, and I'm just sort of putting this blob here to remind me that this is a fixed distribution I'm assuming, and that's something I might want to revisit and check later. Okay, so if I use this model with a slightly updated probability of everything, with this conditional distribution that depends on a variable range, and I also put down a prior distribution on the range, then I can rerun my inference. I have to integrate this thing, and now I've got an extra variable to integrate. It turns out that with this choice of prior, you can still just about do everything analytically, and you can do all these integrals. And here are the results. So we've got the magenta beliefs we had before when we dogmatically assumed that every new star that comes in will come with an enormous range of amplitudes. The gray was our oracle where we knew precisely what range of amplitudes was allowed in the first place. And the blue shows what happens when we infer theta. So we infer the width as we go along, or we integrate it out in the equations. And it's getting quite close to the oracle. So we end up with much tighter beliefs, and they peak much closer to the right answer. This was with 100 data points. If you rerun the simulations with 1,000, 10,000 data points, the blue curve ends up more and more peaked right close to the right answer. So as you learn these parameters, you end up completely pinning down what's going on in the system, and you know the frequency. If you get more and more data, the magenta curve, with its dogmatic prior that refuses to learn, remains broad and biased. So in our graphical model, every time you see another star, you get more observations. You get another one of these nodes. That's great. But you also get 2 more unknowns. So every time you get more data, there's more stuff you don't know. And it's not obvious in a model whether you'll actually ever work out exactly what's going on, because although you have more data, there's more stuff you don't know. If you couple the stuff you don't know so that you can learn what's going on, it turns out that you can become certain of omega. If on the left-hand side you make a wrong assumption about the stuff you don't know, not only can you remain uncertain about omega, but you can actually come up with wrong beliefs. So in other models, you can end up completely peaked on the wrong answer, because every time you see a new observation, you again make a wrong assumption and you never fix it up. So again, don't write down graphical models with parents inside plates. Okay, so here this is a synthetic example. I just generated data from my model, or from something that my model can represent. It's interesting to apply things to real data where you don't know precisely what's going on, and see whether the technique sort of actually holds up. So the next step with the astronomers was to get some data actually from the universe rather than from inside our heads. But we still wanted a system where we knew the correct answer, we knew what was going on. So the system we decided to look at was our solar system. I like the way that this building has sections of the building called Mars and Venus and things. So with this, the next few slides are going to be about Mars and Venus and the Earth and the other 8 major planets. We excluded Pluto. And these planets that are orbiting around the sun, as I said, behave a bit like stars orbiting around a black hole. They experience an acceleration law. So if you've got a planet, it experiences an acceleration depending on its distance from the sun. That acceleration law is an inverse square law, so alpha is 2. That's how gravity behaves. And the constant of proportionality in the force law depends on the mass of the sun and big G and other stuff to get your units right. So what we did in this project was something a bit weird. We took a snapshot of our solar system. So we pretended that we couldn't look at it for long enough, like Kepler did, to see that there are these nice closed elliptical orbits. And all we saw was the positions of the planets and which way they're moving. So we took a snapshot on April the 1st of some year and looked at where the planets were and where they were going. And we pretended that we didn't know that it's an inverse square law. It could be an inverse 1.9 law for all we know. And we pretended that we didn't know the mass of the sun. And we're pretending we don't know those things as a proxy for not knowing what forces a star is experiencing when it could be around a complex matter distribution and experiencing dark energy and dark matter and all sorts of stuff. So is it possible to recover the fact that there's an inverse square law in the mass of the sun from this incredibly limited data of 8 data points containing a position and velocity? So I won't go through all of the details, but we write down a model of much the same form as before. Our observations are distance from the sun, tangential velocity, radial velocity. There are these common parameters that all the planets experience the same force law, but each planet has its own phase. It's in a different part of its orbit. Different planets have different binding energies. That just means some planets are further away from the sun than others. And different planets have different eccentricities. So some planets are nearly circular in their orbits. Some planets have much more squishy elliptical orbits. If the eccentricity was 1, they would be doing this one-dimensional simple harmonic motion. None of the planets are actually doing that. So we write down this model over all the stuff we don't know about the orbits. We put down hierarchical priors on these things we don't know. It turns out that all of the planets in the solar system have orbits which are nearly circular. I mean, you're always told in high school that they have elliptical orbits, but if you draw those ellipses, they're very, very close to circles. So we can learn that from the data. We can learn that that range over eccentricities is actually very small, but we don't want to put that in as knowledge. We're pretending we don't know. So we'll put a vague prior over what that distribution could be like. Okay. So if you turn the handle, you write down the joint probability of everything, you do the integrals, which are a complete pain and cover pages of maths, and you end up discretizing some things to not do quite so much time with Mathematica. You end up with this posterior. So the y-axis is the mass of the sun measured in units of mass of the sun, and then we took log. So the correct answer is 0, because the sun is 1 solar mass, and the log of that, log of 1 is 0. And the correct force law is we have an inverse square law, it's 2. So the correct answer is sort of near a peak of our posterior. And our 95% and 99% credible intervals are sort of safely around the right answer. We're not ruling out the truth. So this work was done in the context of, Bayesian methods won't be able to solve this problem, and there's existing frequentist work on how to do it. So what I'm showing on the right as a comparison to say that this result is awesome is that we've got confidence intervals from sampling theory ways of solving this problem. So we posit a mass of the sun and an exponent in the force law, and then we do a hypothesis test to try and reject that by saying, no, that leads to suspicious coincidences when you sort of look at the consequences of that assumption. And we did it 6 different ways. No matter how you cook up your confidence tests, you end up with incredibly messy and broad confidence intervals compared to a quite nice, compact, credible interval. Here we had to be quite creative and come up with all sorts of different tests we could do and different ways of combining those tests and doing multiple comparison checks. Here we just wrote down the system, did some integrals, and we're done. There's sort of no choices. So this was a sort of point in the paper where we're smug Bayesians and we say, oh, you know, this is all very nice and it's natural and stuff. And if you're ever a smug Bayesian, people are going to smack you down and say, no, it's terrible. So they would say things like, oh, you're making all these assumptions. You wrote down this graphical model and you made strong assumptions because you had these priors here. They don't care about the fact that you put a prior on the force law and things because these are just individual numbers. And it doesn't matter what prior you put down, you're going to get more or less the same answer. But these hierarchical priors, people are going to complain about and worry about. So there's this number here, the eccentricity, which varies between 0 and 1, saying how squishy the orbit is. And our prior on the eccentricity looked like this. We said there's a distribution over the eccentricity, and it could look like this. It could be uniform over this range. It could be uniform over a different range. It could be a taller, skinnier uniform distribution over a different range. We don't know. So we have this prior that says you have a distribution of this form. It's uniform, but we don't know the bounds of the uniform distribution. And that was the prior we used to get the figure. And a reviewer said, well, that's an outrageous choice because the true distribution over eccentricities comes from the way that the solar system formed. You know, if you have a star attracting planets, they're going to fall in a certain way, and that will lead to certain shape orbits. And whatever that physical process is, and we don't want to write down a model of all of that, is not going to give a distribution with these sharp edges, so the top hat. So this prior is almost certainly wrong, and that's going to affect your results. So what we were goaded into doing was coming up with a complicated non-parametric prior that didn't make strong assumptions. So we could say this probability distribution over eccentricities could look like this, it could look like that, it could even look like that, it could look like anything, and we need to put a prior over all of these possible histograms of what the distribution over eccentricities could look like. As an aside, I thought that this was totally ridiculous. We have 8 data points. If you see 8 data points on a line, so let's number the eccentricity, and I go 1, 2, 3, 4, 5, 6, 7, 8. Infer the distribution that those crosses came from. You can sort of say, well, there's sort of a distribution around here. But you can't say, oh, yes, the distribution is that. There's just very little you can say about the shape of the distribution from limited data. And we don't even have these data points. These are things we're inferring which we don't even know where they are within our model, let alone like concrete crosses on an axis. So to sort of do anything more than say, yeah, there's some density roughly here, I didn't think there was really any point. But you know, you appease reviewers, so you go away and you implement a Gaussian process prior on the shape of this thing. And then you can't do the integrals anymore. So you have to do approximate inference using techniques that I'll talk about in future lectures. You turn the handle to approximately do all of the integrals. And annoyingly, it did actually make a difference. So here is the posterior over the exponent in the force law. So the correct answer is 2. And on the left, I've got the posterior given this prior that said the eccentricity is flat over some range. And there's a little peak at the right answer of 2, and there's a bigger peak somewhere else. It's interesting psychology here, because people look at that distribution and go, oh, it's wrong, because you've got a peak at the wrong answer. But you know, that's not how beliefs work. It's like, I've got a load of belief around the right answer. And if the way things worked was that the right answer was always at the highest peak, then you could just throw away all your other peaks. And so, you know, this is the beliefs, and that's how it turned out with this data set. On the right is the results using this Gaussian process stuff embedded in the model that makes less strong assumptions. So I say, instead of being dogmatic and saying, I know that this distribution is uniform, I'm saying this distribution could have any old shape, and I really don't know, and I'm going to consider loads of different options. Adding that uncertainty to the model ends up with a peakier posterior over the things I care about, which is a bit weird. So there's this very narrow spike at exactly 2 that happens to sort of be correct, and you get a higher density at the right answer than we did before. So the scales on the y-axis aren't the same. In some ways that's good. It's like if you're allowed to write down super complicated models, even if you only have 8 data points, and it does actually help. It's a bit worrying because my results seem sensitive to choices of prior where I really don't know what the right answer is, and I'm just making stuff up. What I'm comforted by are the vertical lines on the plots. So the vertical bands are showing 95% and 99% credible intervals. So where is 95% of my posterior mass? And those vertical bands are in the same place no matter which prior I use. And in fact, I tried about half a dozen different hierarchical priors with a load of different choices, and these vertical bars basically didn't move. So these double peaks, they changed their relative heights, and the details changed a bit. But the basic conclusion, which is, yeah, this exponent is somewhere between about 1.99 and 2.05, is incredibly stable, and we can confidently say that from the data. And if you publish a paper, you don't tend to publish the whole complicated details of the posterior that you can't stand behind. You tend to say, well, I think this is my guess, plus or minus something, and that's stable. So it's definitely a good idea when you write down a complicated model to go in and say, okay, there's a bunch of stuff here that I just made up. I should try different choices and I should see what happens to my results as I change those choices. And if my results did change a lot, then I'd have to be worried and I'd have to be honest and say, really we just need more data or different data because we can't be sure we're leaning too much on our assumptions here. Okay, so on my website, these slides will go online, so you'll be able to get this link. There's a practical exercise that contains the maths of the 1D example. It also contains how to put in a more flexible prior and do some Monte Carlo, and it contains a link to the paper on the solar system. So if you wanted to follow through any of the details or check that you can integrate these delta functions or do change of variables, you can do that in your own time. Question?
Can someone argue that with so few data points and by trying out so many options for your prior, you're somewhat overfitting your data?
Yeah, so there is a worry that when you've got one small data set, that when you read a paper, you don't know what they actually tried. I can tell you that honestly, this was the first plot we produced. That was from the first obvious choice of the data. And we didn't go fishing for all sorts of different options. And in fact, one of the complaints that one of the reviewers said was, you shouldn't put this prior on E, you should put the prior on the square root of E, and he had a physical argument for why that was a more sensible thing to do. And it turned out that if you went away and did that, you got better results. The distribution was tighter and a bit closer to the right answer. But I didn't want to rewrite the paper, putting it on the square root of E, because if he'd have said that and it hadn't made things better, we wouldn't have changed it. And I was a bit worried of this cheating effect that you're saying, that when you are comparing against your final test metric, there's a temptation to only make the changes that improve that. And for that reason, we stuck with this choice. However, if you put into your model, it could be good to put a uniform prior on E, or the square root of E, or the square of E, and I have no idea which, and I will infer that discrete choice of which of these is the best prior and put that in as an integer variable and sum over it, then you basically get the same result as the Gaussian process. So it's true that you can't infer much from 8 data points, but you can get a little bit of skew, and that's what putting the square root in does. So I'm quite comfortable with sort of adding in more choices and letting the data pick amongst them. I'd be a bit more suspicious of just hard picking a choice, which I've made by a cheating look at my test performance. Yeah.
In your case, since the solar system is well known, you could have just picked 8 new data points and checked the square root of E hypothesis.
Yeah, so there was this, the question is, we know how the solar system works, so we could have generated 8 different data points and checked. In fact, we did do exactly that. So here I can say, oh, my posterior distribution is peaked around the right place. Something I did was generate a lot of synthetic data sets, run this whole process multiple times, and check that, for example, the correct answer was within my 95% confidence range about 95% of the time, and that turns out true. But all that's happening when I do that is I'm checking my code, and that's an incredibly valuable thing to do, because most code I write is wrong first time, and the reason I did all of that is because I know that, and it's a way of checking my code. But if I've implemented everything correctly, I kind of know that's going to come out to begin with. Here, the data aren't actually drawn from my model. So my model assumes the planets don't interact at all. And that's not actually true. So especially the outer planets, there's some interaction between those. And that interaction is actually somewhat to do with why there's this weird second peak in there. So some of the details of this are artifacts of there being weird things going on. So I was going to say this later, but I'll say it now. One of the things that you should be really looking to do when you're building models like this is, are there ways of checking them? So I made this strong assumption that these phases were all independent. There was no crosstalk amongst the bodies that would cause them to tidal lock and have the same phase. So my prior says any collection of phases is equally good. something I could do, which is not Bayesian at all, it's totally frequentist, is do my inference and not just infer these things, but also infer the phis and have a look at what phases I infer. And if after I've inferred the phases, they're all really bunched up, and my prior said they shouldn't be, I've got some evidence, as in the sort of hypothesis testing type of evidence, that my model is wrong. I can say, well, that's incredibly suspicious, and at the 0.05 level, maybe I should go and look at my modeling assumptions. So a lot of these distributional assumptions that you make, especially when you have a bit more than 8 data points, you can go and check. So if you're going to run this sort of procedure across many bodies of stars, you could begin to see whether these assumptions you're making are true. And what that might cause you to do is write down a more complicated model and then sort of go back and refit. Okay. Are there any other questions? Because I'm going to pause there. Yeah.
The question I have about inference is that it's like generally like a system of equations where the number of unknowns is more than the number of equations. So how far we can go with this?
So the question is, when you're doing inference, you've got more unknowns than equations. So in these examples, my unknowns, every time I got a new data point, I introduced more observations, but I introduced the same number of unknowns. And so I always had one more unknown than I had equations, but only one more. And so it seems like there's not a lot I can do. I think there's no easy answer to how many extra unknowns you can deal with. So I started off with only having a few more unknowns than observations. When I went all non-parametric, though, I suddenly had an awful lot more unknowns than equations. So I said, I represented these distributions as arbitrary histograms. I discretized this line, and I represented distributions with 100 bins, which could be placed anywhere and have all heights. So I introduced an extra 100 free parameters, and my final results ended up more certain than without those free parameters. So there's not an obvious direct relationship between how many unknowns you have and how certain you'll end up at the end. It's a complicated interaction between, well, do you have good prior knowledge about how those unknowns might be tied together? Where are they in your model? And all sorts of other things. So I'm afraid I don't have an answer to the question. Okay, so I'll stop there. What I'll do in future lectures is I'll talk a bit more about these graphical models, the choices you make in them, different types of graphical model, undirected graphical models, and then Monte Carlo inference. How do you go about dealing with things like putting a Gaussian process into your model so you can no longer do all the integrals by hand? Time for coffee.